All right, today I want to give you a chance to look at these guided notes again from 1.1 in our Algebra 2 Essentials course. We're going to talk about primes and factors and factor trees. So the first blank here, two natural numbers. Remember, those are like just your counting numbers. So those nice whole numbers. We're not talking about zero today. They form a factor pair if their product equals a number. So remember, product is the answer to a multiplication problem, so keep that in mind. Now, if you have a natural number bigger than 1, it always has at least one factor pair, 1 and itself. So let's practice doing some factor pairs. So some of these are easier than others, right? 15, well, 1 and 15. You can also do 3 and 5, right? For 2, you're kind of stuck, right? It's just 1 and 2. 37 is the same way. Kind of an odd number. Well, it's odd, but it's also kind of unique, right? Because it's a bigger number, but nothing goes into it except for 1. So those numbers have a special name. They're prime. Okay? So 2 and 37 are prime. The other numbers here are composite, right? So composite is kind of like the opposite. It's not the opposite of prime, but it's the other name that we have. So 40 is composed of other prime numbers, right? So we could list those, and we're going to practice that later, but it's got all these nice factor pairs, right? There's plenty of them. 1 and 40, 5 and 8, 4 and 10, and so on, right? So if something has more than just one natural number has more than one factor pair, we'll call that composite for now. So these blanks here, prime number always has 1 in itself. So there are 12 prime numbers between 0 and 40. I encourage you to find out what those are. But as you're working, you might ask, well, is 1 prime? It's not prime. And hopefully by the end of the video, you'll understand why. Okay? So blank here is primes again, because a composite number, right, remember, is composed of primes. So primes are kind of like Legos, right? They're these building blocks. And when you put them together, you make these bigger composite numbers, right? And a tree, factor tree, is a great way to visualize that. So there's more than one factor tree for 100, but this is one way to break it down. 10 and 10, and then eventually with these trees, you're going to reach prime numbers, and we're going to circle those. And down here at the bottom, I want to summarize. 100 is the same thing as 2 times 2 times 5 times 5. Now, it's maybe looks a little weird to write it like that, but we like that because 100 is composite, right? It's kind of complicated, but we can break it down into just 4 primes multiplied together. And there's something that's kind of powerful about that, right? So I think you guys have had factor trees before, so I'm kind of going a little fast through here, but there's one factor tree that you could do for 32. And it looks like there's 5 2's, which of course we can write with an exponent of 5. Either one is fine. Okay? Now, let me just play with 21 for a second, right? Could I do this? What do you think? Well, I mean, I guess, right? I guess you can. I mean, it's not wrong. But then couldn't I just do this? And then this. And then this. And just keep going forever. So that's, that looks pretty bad. Like, we don't want to do that, right? So that's part of the reason why 1 is not prime. Because remember, factor trees, we're circling those primes at the end. So if we let ourselves write the number 1 in a tree, it could go on forever, right? And that's definitely something we don't want. So this tree is complete nonsense here. So I'm going to erase it. What do you think the real tree is? Pause the video. 3 and 7, right? So letting 1 be prime opens the door into a whole bunch of problems, right? Especially with these trees. Okay, so that was that section. let's talk a little bit about the unique factorization theorem, which sounds really complicated, but I promise it's not. So every natural number, our counting numbers, bigger than 1, so ignoring 1 from the conversation, it's either going to be prime or composite, right? But we just learned up here, like with 100, you can write a composite number as a product of primes. And because we're excluding 1 from the conversation, that product is actually unique. So for example, if I wrote this down, what does that equal? It equals 100, right? But it looks different, right? The structure is different. There's 5 numbers instead of 4. So mathematicians were like, well, this is redundant, right? It's extra. We really don't need to be doing that, right? And that's where this theorem comes into play. And they had to prove such a thing. It's hard to prove why this is true, but we can kind of see with these examples that it makes sense that there should only be one way to break it down. It makes it easier for us, right? Or else we would have a bunch of ways to write 100, right? We already have a lot of ways to write 100, but this theorem's guaranteeing the fact that there will only be 4 primes that make up 100, okay? I'm gonna skip around here. This is a space for you to practice drawing some trees for 36. So you can practice there if you want. But if you did a bunch of other trees, like maybe try 2 and 18, and then break that down. But I think you'll realize at the end of the day, the equation here, 2 times 2 times 3 times 3, will show up in any tree that you make, okay? And then down here, you don't have to worry too much about this. This is just extra. If you like using your calculator for this sort of thing, you can. So like for 81, try and divide it by 2. You can't, so 2 is not a factor. Try and divide it by 3. Well, remember, we always have 1 and 81. 1 in the number is always a factor pair. 2 didn't work because it's an odd number, but 3 I think would work. So, and you don't need to know mentally like what the other factor is. You use your calculator for that. So 81 divided by 3, if you try that, you'll get 27, right? And you can just keep trying numbers. Try 4, try 5, try 6, try 7, try 8. When you try 9, you'll realize, oh, well, yeah, 9 times 9 is 81. What I'm trying to get at step 5 here is that once you get to a point where the number that's written here is like bigger than the square root of the original number, you know you can stop, right? Because without step 5, like we would just keep going. We'd try 10, try 11, try 12, try 13, try 14, and we'd be here forever, right? So a little trick is that you can stop once you go past the square root of that number, which is 9. So we know that once we hit 9, we're done calling it. Those are your factor pairs. Okay, thanks guys.